Hello everyone. I wanted to record the Lesson 13, Chapter 13, Inferential Statistics in Healthcare lesson for you. A few other things I just want to make note of as far as expectations. Go ahead and work on the discussion for me, as well as the chapter review. We'll go over that toward the end of the lecture. So I wanted to go ahead and bring up the PowerPoint and swap these to go ahead and get us started. And so with inferential statistics, we've already talked about descriptive statistics, and we know that descriptive statistics are, they describe the information, the data that you're working with. And the textbook on page 309 talks about that terms such as mortality and morbidity are examples of descriptive statistics. When researchers in healthcare are utilizing, when they're doing research, they're having to infer information, what they're going to glean from the information they are able to obtain. And so using different methods such as the null hypothesis, confidence intervals, and so forth are ways for them to get around having things as descriptive statistics would imply. And so on page 310, we are looking at the standard error of the mean and confidence intervals. And so let's see, understanding, we talked a little bit already about the standard deviation from the mean, and having that, you're going 68% sure that an interval is one standard deviation from the mean or the average. There's two standard deviations 95% of the time when you're working on statistics, this information, that the information will be two standard deviations from the mean or average, and then you have a 99% possibility of it being three standard deviations from the mean. So we're going to be talking about that today as well. So when we look at the characteristics of the population, we're going to take samples of that information, because there's no healthy way to grab all the data at one time, because if you're, especially depending, and it depends on the size of your population, of what you're working with, you might be able to pull the whole grouping of information and utilize the whole thing to come up with your hypothesis or your research, proving that you're accurate in what you believed your research was going to convey. And so once we're looking at on page 310, the standard error of the mean and confidence intervals. So it mentions in that first paragraph, determining the characteristics of a population by taking many large samples, calculating the mean or average for each sample, and then finding the standard deviation of all the sample means. It's called the standard error of the mean, abbreviated capital S, capital E with a small m. Comes from the standard deviation of many sample means. So look down at they've got a 1 sampling underneath there. The data may be displayed in research reports as follows. And our mean is 150, our standard deviation is 10, the number of observations is 75, and the standard error of the mean is 1.15. So we've got all that data, so what do we do with it? What we're going to do is we are 68% sure that one standard deviation would be from the mean would be occurring with this confidence interval, abbreviated CI, capital C, capital I. So if you look at the bottom of page 310, you'll see that the mean, 150, minus the standard error of the mean, 1.15, equals 148.85. If you add the mean and the standard error of the mean together, you get 151.15. So that's one confidence interval on either side of the mean. So, or of the standard deviation. So seeing that, and then you go to the next page, page 311, we are 95% sure that the interval 147.70 to 152.30 contains the population mean. And you'll see that that basically is taking that same mean of 150, subtracting 2, because you're taking 2 standard deviations from the mean, taking 2 times 1.15, the standard error of the mean, and you're going to get 147.70. Similarly, with taking 150, which is the mean, and adding 2 times the standard error of the mean of 1.15 gives you 152.30. And so those are 2 standard deviations from the mean, and with this our mean is 150. And so it doesn't have it on your page, but to get to the 99%, it would be 150 minus 3 times 1.15, and then 150 plus 3 times 1.15, which gives you anywhere from 146.55 to 153.45. That's your 3 standard deviations from the mean. So that's our confidence intervals. They show on number 2 on page 311, the data may be displayed in a research report as follows. And they give you the mean of 60, the standard deviation of 4, the number of observations is 16, and the standard error of the mean is a 1. And so basically you're taking the 1 and either you're adding it or subtracting it from 60. That gives you that 68% confidence interval. To get to 95%, you're taking and multiplying, you're taking the 60 plus, or 60, excuse me, minus 2 times 1, and that's going to give you 58, and then 60 60 plus 2 times 1 would give you 62, and that would be the same 3 times 1, 60 minus 3 times 1, and then 60 plus 3 times 1 would give you 57 to 63. So you see the process there to get us to the confidence intervals for the particular mean and that particular standard error of the mean. So that's what we're looking at from the standard error of the mean and confidence intervals for this particular chapter. And I highlighted this on page 311. It is important to note that the larger the sample size, the more confidence there is in the mean and the smaller the chance for sampling errors, meaning a smaller standard error of the mean. Further, the more homogeneous a population, less variation, the smaller the standard error of the mean. In fact, if a population were all the same, no variation, the standard error of the mean would be 0. So the more variation you have, the more chances that you could have sampling errors. But the larger the sample size, that's going to help you actually grab a good idea of what your information is trying to, what kind of research you're trying to come up with. So for exercise 13.1, I want you to take a look at this with me. You've got your mean of 14, standard deviation of 2, you've got your number of observation as 30, and your standard error of the mean as 0.4. So what are we doing with this? We're going to take, for the 68% confidence interval, we're going to take the 14 mean, we're going to subtract it from the standard error of the mean of 0.4, and we're going to get 13.6. Likewise, we're going to take the mean of 14, we're going to add the standard error of the mean of 0.4 and get 14.4. And so for the 95% confidence interval, it will be, you're taking the mean of 14 and you're subtracting it from 2 times 0.4. That gives you 13.2, and then you're taking the mean of 14 minusing 2 times 0.4, and it gives you 14.8. And then with the 99.7% confidence interval, it will be 14 14 minus 3 times 0.4 will give you 12.8, and then the 14 plus 3 times 0.4 will give you 15.2. And like we've talked about in the past, the answers to the odd questions, odd exercises are in the back. So in case you get stuck on all that. So on page 312, let me click through this. Let's see, confidence intervals, the null hypothesis. Okay, this is where it gets a little word tricky when it comes to trying to determine a null hypothesis. So, it describes the null hypothesis as it states the difference between two population means, that is 0. This statement is generally made based on two sample means. For example, let's suppose we obtain the sample heights of 15-year-old girls at high school A and a second sample of the heights of 15-year-old girls at high school B. These are the means, or the averages. High school A, 5.7 feet. High school B, 5.6 feet. From these results, it would appear that 15-year-old girls at high school A are taller than 15-year-old girls at high school B. However, this may not be true. In fact, the difference may be due to errors in sampling. Maybe they didn't get enough young ladies sampled. They didn't get enough heights to really get a decent sampling. And the mean of the heights of the girls at high school A, population mean, may equal the heights of girls at high school B, population mean. A statement of the null hypothesis would be, and it gives you, the null hypothesis can be expressed as follows. You can see that there on page 312, and where I want to say umlaut, but I know that's not right. Hold a moment. All right, so I went to go look up that that symbol of that U with the long left tail. And I know it means it's a population mean symbol, but I thought that it had another term to it, a Greek term to it, the Greek language. So we're still on page 312. And in the middle of 312, it talks about when conducting research, most researchers are searching for differences in population means and therefore not looking to confirm the null hypothesis. In fact, most research is carried out to reject the null hypothesis. So keep that in mind. Most research is carried out to reject the null hypothesis. Therefore, researchers may develop an alternative hypothesis to test against the null. The alternative hypothesis can be expressed in one of 3 ways. So it gives you the 3 variations that it can be expressed. So on page 313, because there's always a chance that the null hypothesis is true. So a null hypothesis, we talked about it being the difference between two population means is 0. So think of it this way: null is 0. So hypothesis, you're trying to determine if the difference between two populations is 0. So when you're doing your research. So there's always a chance the null hypothesis is true. Testing it will lead to probability, little p, that it is true. The smaller the p-value, probability that the null hypothesis is true, the more evidence that we should reject the null hypothesis, as a rule of thumb accepted by most statisticians in hypothesis testing. If the probability that a null hypothesis is true is 5% or less, the null hypothesis is rejected. That 5% or less is important, so keep that in mind. So the probability, so you'll see through the 3 little samples there, a p is less than 5%. The probability that the null hypothesis is true is less than 5%. P value, the probability value, if it's less than 1%, the probability that the null hypothesis is true is less than 1%. And if you have a probability value of less than 0.1%, the probability that the null hypothesis is true is less than 0.1%. So you can see how that reduction can make your probability options change. And it also states where p equals the probability that the null hypothesis is true. In other words, that the difference between the two population means is 0. So you're trying to reject that possibility, and so that's why the probability, the null hypothesis is true that there's no difference between your two populations is true is less than 0.1%. So you're trying to have the lower probability if you're actually trying to disprove that your sample populations are actually have no difference between them. So remember, we are generalizing from a sample to make conclusions about the population. These different probabilities represent different statistical significance levels. The lower the percentage that the null hypothesis is true, the more significant the finding. Thus, a p of less than or equal to 0.1% is more significant a finding than a p-value of equal or greater than 5%. So, looking at exercise 13.2, I want to talk about what we're doing with the given the following probabilities that the null hypothesis is true, determine whether to reject the null hypothesis or fail to reject the null hypothesis. So we've got a p-value of less than 5.8%, and we know that if you look above that exercise 13.2 header, you've got your p-value of less than 5%. Probability that the null hypothesis is true is less than 5%. Probability that the value is less than 1% is true is less than 1%. And the probability that the null hypothesis is true is less than 0.1% when you have the p-value of less than 0.1. So looking at that information there, and then down to exercise 13.2. So your p-value of less than 5.8%, what would you do? Would you fail to reject the null hypothesis, or would you reject it? You would fail to reject the null hypothesis. It's because the probability that the null hypothesis is true is less than 5%. So you're going to fail to reject it. So if the p-value is less than 0.7%, what are you going to do? You're going to reject the null hypothesis, and that is because that value is the lower the value. Remember that the lower the value, the chance that there's a significance to it is important. So you're going to reject the null hypothesis. You're able to determine a statistically significant finding the closer you get, the lower you get in your numbers. So for number 3, the p-value of 0.15%, you're going to reject the null hypothesis. Same thing for number 4. The p-value of less than 2.6%, you're going to reject the null hypothesis. So number 5, which probability above is the most statistically significant? So looking at all of those numbers, which basically is the lowest number is what you're looking for. And that would be the number 3, 0.15%. So that is exercise 13.2, discussing the probability and how it affects and is it statistically significant. So that is extremely important when you're handling your research. All right. So, and this is a great screen for this. The lower the percentage that the null hypothesis is true, the more significant the finding. So, for example, a p-value of less than or equal to 0.1% is much more significant a finding than a p-value of less than or equal to 5%. And like I mentioned before, most research is carried out to reject the null hypothesis. They're wanting to disprove that there is no difference between two or whatever populations they're trying to determine. Usually it's 2. The 2 types of errors. So we're going to get into type 1 error and type 2 error. So type 1 error, a researcher rejects the null hypothesis. In other words, the researcher rejects, determines basically that there's no difference between the two populations. When the null hypothesis, there actually is no difference between the two populations. So the researcher rejects the null hypothesis when the null hypothesis is true. So in other words, that's wrong. The type 1 error that's wrong is that the researcher rejected that there was a difference between the two, that there was no difference. The researcher rejected that the null hypothesis, which was that meant there was no difference between the two populations being researched, when actually there was no difference between the two populations. Type 2 error, the researcher accepts the null hypothesis when the null hypothesis is false. So the researcher accepted that there was no difference between their two populations, but actually there is a difference between the two populations. So thinking of that in that way between the type 1 and type 2 errors makes it a little easier to understand. All right, so for exercise 13.3, we go back. I'm going to just talk this one out. Use the following information to provide an example of a type 1 and type 2 error. So a pharmaceutical company tests a promising new medicine designed to lower cholesterol when taken daily. The pharmaceutical company conducts a study to determine the effectiveness of the medication against a placebo. Consider the null hypothesis. There is no difference between the effectiveness of a new medication and the placebo in lowering cholesterol. So what they're doing is they're taking saying there's absolutely nothing different between those two types of medicine. Which one is, we know placebos are like a sugar pill, something fake. But the people in the study don't know that. So a type 1 error for this would be what you would see this as for a type 1 error. Okay, the null hypothesis that there is no difference is rejected, but it is true. So that there's basically the null hypothesis is there's no difference between the two medicines, quote unquote, but it's true. It is determined there is a difference between the effectiveness of the placebo and the medication, but in fact there is no difference between their effectiveness in lowering cholesterol. You would know that's not true, as far as that's why this is the null hypothesis that there's no difference is rejected, but actually it's true. That's the reason that this is a type 1 error, is because it's saying, but it is true. So the determining that there is a difference between the two proves that that is a type 1 error. And a type 2 error, the null hypothesis is not rejected, so there's the null hypothesis of that there's no difference between the two is not rejected, but yet that is a false error. It is determined that there is no difference between the effectiveness of the placebo and the medication, but there is in fact a difference between their effectiveness in lowering cholesterol. I know this sounds a little confusing. Just take a deep breath with all this, but it's almost a way of looking at it kind of backwards. So again, with this being said, let's talk about exercise 13.4. I know we're not there yet because we're still on page 314. So giving the information, the example above, which is the information we just talked about in the type 1 and type 2 error. Would you reject the null hypothesis or not? How would you state your findings? So what you would state is fail to reject the null hypothesis is basically what that would be. So let's go back. So we're basically worked through all the exercises thus far in this chapter, and we'll get on to the review here in a moment. But I want to talk about the t-test. So a t-test is an example. I'm going to read this word for word from the book. Example of a test of the null hypothesis to determine if a set of results is statistically significant. So we've already talked about how the p-value helps us to determine if something is statistically significant. It has to have the probability, the p-value that the null hypothesis is true should be 5% or less. So, and you'll see this in an example in your textbook. And it goes through the two different, has group A, group B, and you'll go through and and I won't go through this in such great detail, but it boils down to understanding the statistic. If you see that statements 1 through 3 above, this is on page 315, all reject the null hypothesis. In other words, they all say no, that the null hypothesis, which says a null hypothesis is saying there's no difference between the two populations. So statements 1 through 3 above all say no, that there actually is a difference, and that there is a statistically significant difference between the population means of Group A and Group B, which gives you the negative 1.3, as it states there. And then it states, however, the sample data may not support the conclusion that there is a statistically significant difference between the means. Consider the following example. And they've got Group A and Group B, and they show you at the bottom of page 315, one, not statistically significant because the p-value is less than 0.05, and the null hypothesis is, excuse me, I said that it was greater than, the p-value is less than, no, is greater than 0.05. And so that's not statistically significant because it's getting further and further away from like a 0.01. So the null hypothesis is not rejected at the confidence level of 0.05, and so on. So, all right. We talked a little bit about exercise 3.4. I'm on page 316. Let's see, that's where I came up with the comment of the you failed to reject the null hypothesis for our difference between the two groups. So, all right, so now we're diving into ANOVA, analysis of variance. So we talked a little bit about variance in a previous chapter, correlation and variance. So now ANOVA test is used to test the difference among two or more means, two or more averages. So on page 316, we've got a variety here at the bottom of males and females. The LOS group 1 and LOS group 2, and patients with private insurance and patients with, oh, that's the length of stay. That's what the LOS stands for. So length of stay for the males with private insurance is an average of 10, and with the length of stay with group 2 males, the average is 23 for their length of stay. And for females, it's 15 for an average with private insurance, and with the length of stay for group 2 with Medicare and Medicaid, it's 17 as an average length of stay. So it's giving us all these means, and what we're doing on page, if you look up on page 317, differences tested by ANOVA. So you've got the variety of what you will test against. You're testing between A and B, between A and C, and how we know which group is which is it's labeled out at the bottom of page 316. And that's just showing you there's 6 variations that you can come up with to test between the two differences to determine if there's any statistical significance between your two populations. So if the results from an ANOVA are statistically significant, you reject the null hypothesis that there are at least one pair of the means is different. The researcher's next step is to figure out what differences are significant. However, if the results are not statistically significant, the null hypothesis is not rejected. The work is done. All right. So chi-square is a test of significance, deals with nominal data and frequencies. And it says under chi-square on page 317, note that calculation is possible but just not meaningful. And you can actually use, I think you use Excel to actually conduct a chi-square test. I call it chi, forgive me, it's chi-squared. And they show an example at the bottom of page 317. Employee whose parents smoked, employees whose parents did not smoke, and so forth. And they show the data in this table suggests that those employees with parents who did not smoke were likelier not to smoke than were those employees with parents who smoked. From this sample alone, there appears to be a relationship between smoking and having parents who smoked. However, there's a possibility that the null hypothesis that the relationship does not exist in this population is true. A chi-square test can determine whether the relationship is statistically significant. A chi-square test using the values above yielded these results. And so you can see that they have the x with the power to the 2, which is actually chi-squared, 10.71. Forgive me, let's see, the degrees of freedom equals 1, and the probability is less than 0.01. So that's showing that p-value of 0.01 that is statistically significant. Top of page 318, it shows that based on the results there is a less than 1% chance that the null hypothesis is true. Said another way, the results are statistically significant. There is a relationship between employees who do not smoke having parents who do not smoke. Notice how the degrees of freedom are determined differently for chi-square. The degrees of freedom are found by taking the r-1 times c-1 for the number of categories, where r equals the number of rows and c equals the number of columns. So that basically ends the chapter there. So let's talk about the review. So I won't go over the matching quiz. So the review, let me see if there's any more of our screens here. Okay. So our review. And the majority of this review, you're going to be actually typing in your answers. As you can see, it's more of an essay style. So I'm going to try to keep this short and sweet, and you know, what's the expectations are. So defining inferential statistics, that's actually, you know, it's in your book, and so, you know, this is not a difficult thing to define. So inferential statistics are those that allow us to generalize from a sample to a population with a certain amount of confidence regarding our findings. So that's all I expect for that particular question. Okay, difference between descriptive and inferential statistics. So this should be a no-brainer. You know, descriptive, you're describing data. Inferential, or you're generalizing from a sample to a population. So descriptive statistics merely describe data, period. Inferential statistics are used to generalize from a sample to a population. So very basic, and that's also in your chapter, very easy to find. So now, identify, question 3, which choices would be considered descriptive statistics and which would be considered inferential statistics. So, of 500 randomly selected people in New York City, 210 people had O positive blood. Okay, so that's the main statement. So basically your question A is, for question 3, 42% of the people in New York City have O positive blood. Is the statement descriptive statistics or inferential? So why would this be which one? Well, if you look at it, 42%, very specific. New York City's very specific. O positive blood is very specific. So when you're being specific, when you're not inferring anything, if you're being very specific, you're being descriptive. So that would be descriptive. So question 4. 58% of the people in New York City do not have O positive blood. Is the statement descriptive or inferential? Same thing as the first one. You've got very specific information. You're describing what your information is. 58% New York City, O positive blood. It's descriptive. All right. For C, 42% of all people in New York State have O positive blood. So yes, you have some descriptive information there, but it's not, if you think about the size of New York State, and they're saying 42% of all people, well, you would have to take a sample of those people and to make this type of statement. So you're not really, even though it looks a little bit descriptive, it's not really descriptive. It's actually, you're inferring that all people, at least 42% of all the people living in New York State, very large state, have O positive blood. You are inferring with that statement. So that's why that is what it is. Okay, question 6, which would be actually question 4 in your book. Identify which choices would be considered descriptive statistics and which would be considered inferential. So, on the last 3 Friday evenings, City Hospital diagnosed a number of heroin overdoses. There were 4 on January 14th of 2000 and something, 2 on January 21st of 2000 and something, and 6 on January 28th of 2000 and something. All right, so the first statement, first choice, A, City Hospital averaged 4 heroin overdoses in their ER for the last 3 Friday evenings. Would that be descriptive or inferential? It would be descriptive. Very specific. City Hospital averaged 4 heroin doses in their ER the last 3 Friday evenings. Very descriptive. Okay. B, which is question 7 on your test. City Hospital never has had more than 6 heroin overdose on Friday evenings. That is not real specific. City Hospital never has had more than 6 heroin overdose on Friday evenings. That would actually be inferential. You're inferring that statement with that statement. Friday nights, this is question 8 on your test. We're still actually on question 4 on the review in your book. Friday nights are the busiest time for heroin overdoses at City Hospital. You are inferring. That may be the truth, but you don't know unless you're taking a sampling of those dates and checking for the amount of heroin overdoses and so forth. So you're actually inferring. All right. So, true or false, the standard error of the mean comes from the standard deviation of many population means. That actually would be false. And if you had stated the standard error of the mean comes from the standard deviation of many sample means, that would make it true. So the word population makes it false. For question 10, which is actually question 6 in your book, create a null hypothesis for the following research question. What are the differences between emergency room shifts on medication errors? So, and because we're creating a null hypothesis, we'd say that the null hypothesis is there's no difference between emergency room shifts on medication errors. So basically what we're trying, remember, the null hypothesis is saying, always stating, there is no difference between our two samples, our two sample populations. So our two sample populations, there's no difference between emergency room shifts on medication errors. So we know there's a variety of shifts for the emergency room, and so that's our sample populations, and so that's why that is the statement. There's no difference between emergency room shifts on medication errors. So question 7 in your book, but question 11 on the review. Create a null hypothesis for the following research question. On a clinical trial of a new drug, what will be the effects over a currently used drug? So your null hypothesis would be there would be no difference between the currently used drug and the new drug. So basically what you're trying to say with that, that's for the clinical trial of the new drug, that a null hypothesis is stating there's no difference. Remember that. Null, zero difference. Null hypothesis, there's zero difference between an old drug and a new drug, basically, or a currently used drug and a new drug. So that's why your null hypothesis would be, which means there would be no difference between the currently used drug and the new drug. That's your two. The currently used and the new drug are the two different populations. On question 12 on the review, and that's actually question 8 in your book, reword the following research hypothesis to a null hypothesis. Smoking during pregnancy increases the risk of a child being born prematurely. So that's a statement. You're trying to create a null hypothesis. You're trying to show that there's no difference between smoking during pregnancy and a child being born prematurely. So you're wording it to state the null hypothesis. So a null hypothesis statement would be the risk of a child being born prematurely will be the same for smoking pregnant women and non-smoking pregnant women. So you're basically stating there's no difference between smoking and not smoking and causing a child to be born prematurely. So the answer would be, the null hypothesis is the risk of a child being born prematurely will be the same for smoking pregnant women and non-smoking pregnant women. All right. So question 9 in your book and question 13 on the review. Reword the following research hypothesis to a null hypothesis. Regular exercise in older adults decreases blood pressure levels. Regular exercise in older adults decreases blood pressure levels. The null hypothesis would be, in older adults, there is no relationship between regular exercise and blood pressure levels. So a null hypothesis is stating there's no difference. So a null hypothesis would be, in older adults, there is no relationship between regular exercise and blood pressure levels. All right. So question 14 on the review and question 10 in your book. Based on the results below, and this is in your book, so keep that in mind, how would you describe the relationship between heart attack patients being treated with aspirin and whether or not they lived? So you see that in the book on page 319, the bottom of the page, male patients who lived, male heart attack patients treated with aspirin, and then male patients who did not live. You've got 15 who lived and 2 who did not. Under male heart attack patients not treated with aspirin, you have 4 who lived and 8 who did not live. And so you end up with a probability of less than or equal to 0.01. That's statistically significant when you look at that number, right? So your answer for that one would be something to the effect of, when you're stating this, when you're describing this, it appears that patients treated with aspirin had a better chance of living, 15 versus 2, than those not treated with aspirin, 4 versus 8. Just by looking at the table, you can see that more male heart attack patients treated with aspirin lived. However, the chi-square test tells us more, that there is a less than 1% chance that the null hypothesis is true. Basically, that there's no difference between taking aspirin and not taking aspirin. The results are statistically significant. There is a relationship between male heart attack patients who lived and took aspirin. So to answer this, to type this in, this is what you're going to do. This is what I expect. The results are statistically significant. There is a relationship between male heart attack patients who lived and took aspirin. All right. Question 11 in your book, and it's actually question it's a question 11 in your book, yes, and it's question 15 on the review. So, using the following information, determine if the differences between the means are significant. Your medical terminology class, Group A, number of word elements remembered by students using flashcards, and Group B, number of word elements remembered by students not using flashcards. The null hypothesis, there is no difference between the groups. So that's what you're trying to you're stating there's absolutely no difference between your two populations with the null hypothesis. So you've got a probability of greater than 0.01. So is that statistically significant? So looking at those groups, Group A and Group B, you're going to reject the null hypothesis because at that confidence level of 0.01, the statement rejects the null hypothesis and says there is a statistically significant difference between the sample means of Group A and Group B. So that's what that answer would be. You reject the hypothesis because it gives you the probability of greater than 0.01, or less than 0.01. I apologize if I said greater than before. So reject the null hypothesis at the 0.01 level. This is what you're putting on your answer. Reject the null hypothesis at the 0.01 level. This statement rejects the null hypothesis and says that there is a statistically significant difference between the sample means of Group A and Group B. All right. So question 16 on your review, question 12 in your textbook on page 320. Given the following p-values, probability values, which would be considered more significant? Of those, you've got a p-value of less than or equal to 0.3, less than and equal or equal to 0.02, less than or equal to 0.25. You know, we talked about how the closer you come to basically 0, the higher the statistical significance. So which one would you think? It should be B. So make sure you select B. And you'll actually have to type that in. I'll be manually grading this one, obviously, this whole review. So question 17 on your review, question 13 in your book. Given the following null hypothesis, give an example of a type 1 error. All right. The null hypothesis, there is no difference between the number of males or females who go to their primary care physician for an annual exam. So a type 1 error would be, a type 1 error would occur if the null hypothesis were rejected when in fact there is no difference between the number of men or women who go to their primary care physician for an annual exam. So that's the answer. Let me restate that. A type 1 error would occur, OCCUR would occur, if the null hypothesis were rejected when in fact there is no difference between the number of men or women who go to their primary care physician for an annual exam. Okay, that's the answer. Why is that the answer? Because remember, you're trying to show an error, type 1 error, that fits the type 1 error framework. So, and we know that from page bottom of page 313 and top of page 314, a type 1 error, what you're trying to state is that for an just as an example, that let's see how best to state that. Well, type 1 error occurs when the null hypothesis, the null or zero difference between the two samples is rejected, but yet it is actually true. So you're rejecting that there is no difference, but yet there actually is a difference. So well, no, excuse me, you're rejecting that there is no difference, yet you're rejecting there's no difference, but there actually is no difference. And the type 2 error occurs when the null hypothesis is not rejected, yet it is false, which in other words, type 2 error occurs when the null hypothesis, or that there's no difference, is not rejected. So there's no difference between your two, you're rejecting that there's no difference between their two samples or your two populations, but there is a difference. Let's say it occurs when the null hypothesis is not rejected. So there's no difference, so it's not rejected, but yet it is, there is a difference, so it's false. So all that being said, so I gave you the type 1 error. Type 1 error would occur if the null hypothesis were rejected when in fact there is no difference between the number of men or women who go to their primary care physician for an annual exam. We know that there is a difference between the number of men and women who go to their primary care physician for an annual exam. Women typically go more, so that's why this is a type 1 error. So question 18, which is 14 in your book, given the following null hypothesis, give an example of a type 2 error. The null hypothesis is there is no difference in the level of understanding of this chapter between students who had previously taken a statistics course and students who have not previously taken a statistics course. So your answer would be a type 2 error would occur if the null hypothesis is not rejected, when in fact it is false. In other words, a type 2 error would fail to reject the null hypothesis when in fact there is a difference in the level of understanding of this chapter between students who have previously taken a statistics course and those who have not. Let me repeat myself. The answer would be a type 2 error would fail to reject the null hypothesis when in fact there is a difference in the level of understanding of this chapter between students who have previously taken a statistics course and those who have not. Okay. All right. So the last one, let's see, make sure that's the last one. Yep. Given the following information, determine the 68%, 95%, 99.7% confidence intervals. So, and I apologize, that's supposed to be, those little question marks are supposed to be the mean equals 4.33, and the standard error of the mean equals 3. So we know that you're going to take, to get the 68%, and I want to see the math on this. So make sure you do this with the math on this, because I want it to look like what's in your book on, let's see, on page, the bottom of page 310 and the top of page 311. So, you know, you're going to take your standard deviation, the 4.33, to get the 68% confidence interval. You're going to take the 4.33 and subtract it from the standard error of the mean of 3, and that's going to give you a figure. And then you're going to take 4.33 and add it to 3. That's going to give you a figure, and that's 68%. So I want to see the math on that. I'm not going to give you this answer because you guys, this is simple math. For the 95%, I want to see, and I want it to say like 68% confidence interval, or 68% CI equals 4.33 minus 3, and that give me equals whatever that is, and then 68% CI equals the 4.33 plus 3 equals. So I want to see it in that kind of framework on this particular question. So, and you can see in the chapter for the 95%, you're going to take the 4.33. You're going to take in minus, and in parentheses, you're going to say 2 times 3, close parentheses, equals a number, and then 95% CI equals 4.33 plus, in parentheses, 2 times 3, close parentheses, and that gives you an equal. And so the final one is going to be 99.7% CI equals 4.33 minus, parentheses, 3 times 3, parentheses, equals, and then 99.7 CI equals 4.33 plus, parentheses, 3 times 3, close parentheses, equals. So, all right, that is the end of this review. Like I said, make sure you complete the lesson 13 discussion. Please reach out to me if you have questions, and I hope that you have enjoyed this semester. And thank you so much.